Hello everyone, I welcome you all to the today's session on Introduction to Complex Power Series. Myself, Dr. N.C.H. Ramgopal, working as Associate Professor in Mathematics in the Department of Humanities and Sciences, MLR Institute of Technology, Hyderabad. Today, I am going to introduce the Complex Power Series, Complex Power Series expansion of a complex function of complex variable. So, the introductory part, and then the infinite series of complex numbers, convergence and absolute convergence, and the main concept is the complex power series and the methods to find the complex power series, and in that Taylor's and McLaurin series expansions. Now, coming to this introduction part, here we are going to develop the methods of expanding a given complex function. The methods of expanding a given complex function about a point z equal to a or in powers of z minus a. So, for example, some f of z equal to sin z is given, a function of complex variables. Here, this sin z can be expanded in powers of z or in powers of z minus a. That the same thing can be considered as the about a point z equal to a. So, we expand a given complex function about a point z equal to a or else in powers of z minus a. Actually, both are one and the same. If about z equal to a means if this a comes to the left side, z minus a equal to 0. So, z minus a in powers of z minus a, and this power series expansion is used to expand other functions, to solve given equations, and to provide the assessment of intervals of convergence, and also used in trial functions. So, there are many applications of these power series expansion. For example, if you want to study the nature of a given function, whether it is real or complex, if we expand that like a power series, then it is very easy to study the nature of that function. Hence, it is applied in all areas of science and engineering. So, there are many applications of these power series expansions in both real and complex cases. Now, let us consider an infinite series of complex numbers. Here, I have taken Zn. Sigma Zn is Z1 plus Z2 plus Z3 and so on. Simply, this is sigma Zn where n equal to 1 to infinity. So, there are infinite terms in this series. So, Z1, if you expand n equal to 1 here, put n equal to 1, Z1, n equal to 2 plus Z2, the sigma notation is for summation. So, Z1 plus Z2 plus Z3 and so on. It is an infinite series expansion, and here this is the nth term Zn. Now, for example, let consider Zn as an plus ibn, an ibn, where an comma bn, these are real numbers. These are real numbers. Now, Zn becomes sigma an plus ibn, so which is a1 plus ib1 plus n equal to 2, a2 plus ib2 plus so on. Nth term is an plus ibn itself plus so on. That means it is an infinite series expansion. And here there is another important point, that if the series of real values sigma an and bn, if sigma an converges to capital A, sigma bn converges to capital B, then this sigma an plus ibn, this converges to capital A plus I into capital B. And what is this convergence? A series is said to be convergent if there exists a limit, a unique limit. Divergence means it tends to infinity, either plus infinity or minus infinity. So, a series is said to be convergent if the limit exists and it is unique. And absolute convergence, a series sigma Zn is said to be convergent absolutely if sigma mod Zn is convergent. If sigma mod Zn is convergent, then sigma Zn is said to be absolutely convergent. So these are the basic definitions that we need to know to deal with complex power series. Now, consider the infinite series of complex functions un of z. So here z is a complex variable, z is x plus iy, and we are using that in the function u. So it's a function of complex variables, and series sigma un z, again from n equal to 1 to infinity, u1 of z plus u2 of z plus u3 of z and so on, which is a series of complex functions. Now coming to the main definition, power series. A series of the form sigma an z power n. Sigma an z power n is called the power series, where these an or ais are constants and z is a complex variable. So for example, if we expand this sigma an z power n from n equal to 1 to infinity, infinite series expansion, a1 z, a2 z square, a3 z cube and so on, an z power n plus so on. So this is the nth term. Using the nth term, we can define this entire series using the summation notation. Now the next definition is radius of convergence. If sigma an z power n converges for mod z less than r, for modulus of z less than r, that means the radius of this circle with center at origin is less than this capital R, and diverges for mod z greater than r, then r is called the radius of convergence of the power series. So if the power series converges for mod z less than r and diverges for mod z greater than r, then this capital R is said to be the radius of convergence of the power series, and the circle mod z equal to r is called the circle of convergence. Since this r is the radius of convergence, this circle is called circle of convergence of the power series. Now the important one is the Taylor's theorem, using which we can find the Taylor series expansion of given function. And we have this Taylor series in both real and imaginary, real and complex cases. Even we can expand a real function f of x using Taylor's series, Taylor's theorem, and a complex function also. We can expand the given complex function using the Taylor's theorem. So that expansion is called Taylor series expansion. Now coming to the statement, let f of z be analytic at each and every point within the circle C with center at A and radius equal to r. Then at each point in that circle or the curve C, f of z can be expanded, or f of z can be expressed in this form. What is that? F of a, so that means the functional value at z equal to a plus z minus a into f dash a plus z minus a whole square by 2 factorial f double dash a and so on. So that means here we have z minus a power n, z minus a whole square, in the next term z minus a whole cube and so on, z minus a whole power n. So that means the in powers of z minus a. So this expansion gives the function in terms of z minus a, powers of z minus a. So this is called the Taylor series expansion of f of z about a point z equal to a, or in powers of z minus a. So this series on RHS, this RHS term converges to this f of z when mod z minus a is less than r. That's what we have defined in the earlier case, the radius of convergence. This r is called the radius of convergence. It converges for mod z minus a less than r and diverges for mod z minus a greater than r. So this RHS term converges to LHS f of z when mod z minus a is less than r, and this entire expansion is called the Taylor series expansion of the function f of z about a point z equal to a or in powers of z minus a. And the expansion is also very simple. No need to by heart. Just you need to identify the format. Here the function f of z, we need to expand this, or we need to find the infinite series expansion of this function. So put z equal to a, f of a. So the expansion starts with this constant term f of a plus in powers of z minus a. So z minus a into f dash a. Here we have the power 1 and the first derivative by 1 factorial. Similarly here z minus a whole square by 2 factorial and f double dash a. So these things should match. Here n and n factorial. So if you understand the format of this expansion, no need to by heart. Simply you can write the expansion of f of z. And for given function, to write this Taylor series expansion, simply we need to find all these values. We need to calculate f of a and then f dash a. So first we find the derivative of f, then put z equal to a. Similarly, second derivative, third derivative, that means to find the Taylor series expansion of the given function, first we need to calculate the successive derivatives of the function, f dash, f double dash, f triple dash and so on. Then substitute z equal to a in all those derivatives and substitute here. So f of a we can calculate by replacing z equal to a, f dash a, f double dash a, all these are given by the successive derivatives. Simply substitute here and we can obtain the expansion of the given function in powers of z minus a, or the same thing can be called about a point z equal to a. Similarly, the next one is McLaurin series expansion, and here the McLaurin series expansion is a part of Taylor series expansion or a subcase of Taylor series expansion. Simply, if we take a equal to 0 in the Taylor series expansion, Taylor series expansion is about a point z equal to a, but here a is 0. So if you can find the expansion about z equal to 0, that is called McLaurin's series expansion. So simply the McLaurin series expansion is a subcase of Taylor series expansion. That is the Taylor series expansion about a point z equal to 0 or in powers of z. Previously we have z minus a, the powers of z minus a, but a is 0. So we will get the powers of z only, z, z square, z cube and so on. So the Taylor series expansion about a point z equal to 0 or in powers of z is called the McLaurin series expansion, and it is given by, it starts from f of 0. Previously this is f of a in Taylor series. Now we are replacing a by 0. We are calculating all the derivatives also at a equal to 0. So f of 0 plus z into f dash 0, z square by 2 factorial, f double dash 0 and so on. And again the format, you need to identify the format. Power n, nth derivative, n factorial. Z square, second derivative, 2 factorial. And it starts with the constant f of 0. Next term f dash 0, next f double dash and so on. Here z power 0, z power 1, z square, z cube and so on. Denominator 0 factorial, 1 factorial, 2 factorial and so on. So if you identify the format, no need to by heart the formula or this expansion. Now, to obtain the Taylor series expansion or McLaurin series expansion, we can use the following expansions, the known expansions. Here already informed, we can find both the Taylor series or McLaurin series expansions for both real and complex functions. So this is the main important point. We can expand a real function or we can expand a complex function as a Taylor series or McLaurin series. In both cases we can. So let us consider the real case, the known expansions. Sin x, we know the expansion of sin x, cos x, e power x, all these are the Taylor series expansions itself. In particular, the MLR series expansions about x equal to 0 are in powers of x. Sin x, cos x, e power x and so on. Again, here if you identify the format of that expansion, simply you can write the expansion. So here, what is the value of sin 0? Sin 0 is 0. So the first term 0. It starts from x. Plus minus alternately changes. X minus x cube by 3 factorial plus x power 5 by 5 factorial minus x power 7 by 7 factorial and so on. So format is the main point. X is having only odd powers. So in the expansion of sin x, there are only odd powers of x. First term is x. X minus x cube by 3 factorial. So the power and this factorial must be the same. Plus minus alternately changes. And coming to this expansion of cos x, what is the value of cos 0? Sin 0 is 0, but cos 0 is 1. So it starts with 1. Again, plus minus alternately changes. Here we have odd powers, here even powers. X square by 2 factorial, x power 4 by 4 factorial, 6 by 6 factorial, plus so on. And the expansion of exponential function e power x, e power 0. What is the value of e power 0? 1. Here sin 0 is 0, cos 0 is 1, e power 0 is 1. Why I am asking all these functions at 0? Again, go back to the previous slide. The MLR series expansion starts with the term f of 0, the function at x equal to 0. So sin x at x equal to 0, sin 0 is 0, that's why there is no term, constant term. Cos 0 is 1, so starts with 1. E power x, e power 0 is 1. And the expansion of e power x is having all powers of x. So 1 plus x square by 2 factorial plus x cube by 3 factorial and so on. Similarly, there are some other expansions. 1 by 1 minus or 1 plus x. This is 1 plus x power minus 1. Next, 1 by 1 minus x. 1 minus x power minus 1. So here, again, here we have plus and here minus. So the alternate terms are negative. So first 1 minus x plus x square minus x cube plus x power 4 minus x power 5 plus so on. And here both are negative. So all the terms are negative. The same expansion, all are negative. 1 plus x square plus so on. Similarly, 1 by 1 plus x whole square, which is 1 plus x whole power minus 2. So the expansion is 1 minus 2x plus 3x square minus 4x cube plus 5x power 4 minus 6x power 5 plus so on. So here alternate sign is changing alternately and the quotients are 1, 2, 3, 4, 5 and so on. Similarly, 1 minus x power whole square. So 1 minus x power minus 2, both are negative signs. 1 plus 2x plus 3x square plus 4x cube plus so on. All the terms are positive. So these are in the case of real functions. So sin x, cos x, e power x and the expansions of these. So these can be followed in the complex case also, complex functions. The same thing, sin z expansion. So sin z, z minus z square by odd powers, z cube by 3 factorial plus z power 5 by 5 factorial minus z power 7 by 7 factorial and so on. Cos z, so it starts with 1 minus z square by 2 factorial plus z power 4 by 4 factorial minus z power 6 by 6 factorial and so on. E power z, all powers of z exist. 1 plus z square by 2 factorial, z cube by 3 factorial and so on. Similarly, 1 by 1 plus z, which is 1 plus z power minus 1, 1 minus z plus z square minus z cube plus z power 4 minus z power 5 and so on. Alternately sign changes. And 1 by 1 minus z. If you know this expansion, you can write the next one. Both are negative signs, so all the terms are positive. 1 plus z square plus z cube plus so on. Similarly, 1 plus z whole square. So 1 plus z whole power minus 2. 1 minus z whole square. 1 minus z whole power minus 2. Here 1 minus 2z plus 3z square minus 4z cube and so on. The quotients are 1, 2, 3, 4 and so on, and the sign changes alternately. And here both are negative, so all the terms are positive and so on. So why I am introducing or recalling all these expansions is to expand the given complex function as a Taylor series. First, we write the function in the simplest form, and you can utilize these expansions, the known expansions. So that's why we need all these expansions. So sin z, cos z, e power z, 1 by 1 plus z, 1 by 1 minus z and so on. Maximum up to 2 is enough. If you want, you can refer for 1 minus z whole cube and so on. So using the known expansions, we can expand the given function, or using the Taylor's theorem statement, you can find the Taylor series expansion of f of z. So today I have introduced the power series expansions, in particular the complex power series and the methods to find the complex power series. One of those is Taylor's series expansion and then Maclaurin's series expansion. In the next session, I am going to solve some problems on Taylor's and Maclaurin's expansions. So here, for the given function of complex function of complex variable, we find the Taylor series expansion and Maclaurin series expansion. So that means we expand the given function in powers of z minus a or about a point z equal to a. So we are going to find such expansions in the next session. This is for today's session. We'll meet in the next session. Thank you very much.